So, hello बच्चों, सत श्री अकाल, namaste from my side. So I think this is the second lecture. I think previous lecture went on. I already told you all the glimpse of the basics of the chapter will go on, not the entire. But many students thought like, "Arey sir, this is remaining, this is remaining." Don't get worried. Part 2 of that will be uploaded soon. This is the basics of the second chapter. Okay, we are going to cover the entire chapter within it, the electrostatic potential and capacitance. We are going to cover electrostatic potential, potential energy, right, and everything within it. Okay, so I think without wasting our time, capacitors, complex networks, so without wasting our time, we should move on to it. Come on. So what will be the agendas of today's lecture? The whole capacitors, right? So let's move on to it. Electrostatic potential energy, right? Electrostatic potential how we are going to move forward to that. Okay, how we are going to compare the electrostatic potential energy to the day-to-day life. Let us take an example. Suppose right now I am having cravings to eat chocolate. Cravings to eat chocolate. What I am going to do? Okay, cravings to eat chocolate. Mark my words on the example. Okay, either I'm going to tell my sibling or a brother or a sister who is already into the market with one of his work, I used to just ping him up or ping her up, or I used to call him up or call her up that please bring this chocolate for me. So what happened here? I was not having the chocolate in my home, but as of some cravings, I told one of my siblings to bring that up from outside market. To bring that up from the outside market. Yes or no? Right. You have to remember this example to understand the concept of the electrostatic potential and potential energy. Why? Many students might be into the thought, sir, what is there in special in this example? You are, your sibling, your chocolate, your house. These four things are quite special in this. You, your sibling, chocolate, and your house. These four terms, these four entities are quite important in this example to understand the concept of potential and potential energy. Sir, why you are doing lots of hard work? In NCERT it is written the definition of the electrostatic potential and the electrostatic potential energy appears to be same. For once, right, if we are reading this, we consider both as the same. But from the physics point of view, it differs, na? Okay. So guys, right now moving forward to the technicalities, again we are going to come back to that same example. Okay, but you have to just remember, you cravings of a chocolate, you called up your sibling or brother or sister, right, who is already into the market with one of his work, whether this is important work, and you commanded, you requested him or her to bring up the chocolate because it wasn't available in your house. Right now, let's move on to it. We are having one source charge, right? I told you all into the previous lectures also, there is a special area up to which the effect of this source charge acts. The force of this electrostatic charge, the force of the static charge acts up to the spatial area. That area, it is nothing else but the electric field. That area is nothing else but the electric field. Even I told you all into that case that this is the unbounded area. Unbounded area. I am not aware of the actual boundary up to which, the actual distance up to which this source charge is going to, right, provide or going to attract or repel by its electrostatic force. I am not aware of the area, guys. I am not aware of. But still, I told you all, I compared this to the gravitational boundary of the earth. Okay, whenever the rocket is released from the surface of the earth or from the land, okay, it is released with the thought that it is going to cross the gravitational, right, field of the earth. But I want to ask you all, up to what kilometers we can say this is the edge of the gravitational field of the earth. Beyond this, we are not going to attract within it. It's not like that. Boundaries are not fixed. We can't say up to 1 lakh kilometer, up to 2 lakh kilometer, up to 3 lakh kilometer, only the force of the gravitational force of the earth will act. After that, you are lost into the space. You are lost into the space. It's not like that. Okay. It is an unbounded area. We have to just release the object with the escape speed 11.2 km per second. Finally, you are definitely going to get rid out of this gravitational field of the earth. Okay. And whenever you are far from the earth, obviously the force between you and the earth will be slowly negligible. It tends to zero. Limit tends to zero. Right. Similarly, this is a source charge. This is the area up to which the force of the electrostatics act of this source charge, and obviously this is a unbounded area. The thing that I have drawn, it is only for the understanding purpose. It is just for the understanding purpose, right, guys? Now, there is one charge at infinity. There is one charge at infinity. Source charge, area at infinite position, there is one charge. I got interested in that charge. I want that specific charge into my area. Yaka. But I am fixed. By itself, it is not right. The charge itself can't do the task. Alas. So what did this source charge did? He commanded to external agent. He commanded to external agent by the communication system, alpha to delta, external agent, alpha to delta, external agent. Please do some work for me, please. External agent, okay. I will do you. But what actually the task is all about? The source charge told you have to bring the charge from infinite position to any point under the electrostatic field. He told you have to bring the charge from infinite position to the point P under the electrostatic field. External agent. Oh, this is quite difficult task. External agent told source charge that this is quite difficult task. To bring the object from infinite position to the point under the electrostatic field is the difficult task. It needs lots of amount of the energy. Source charge told, okay, I am gonna make your task easy. You bring that charge in such a way that its velocity remains constant. and change in kinetic energy remains 0. External agent, oh, I think now this is what we can say feasible. Suppose if you are not giving me the condition under the external agent to the source charge, here you are not giving me to the conditions, then it is quite difficult. Because from infinite point to the point under the electrostatic field, lots of variations into the energies are there. Then how I am going to balance those variations? It is difficult, na yaar. You are just going to give me the call. Wrong, na yaar. For source charge, external agent did that work. Mark my words. Now I am going to compare this example to the day-to-day life. Source charge at the home, cravings of the chocolate. He want that charge to be inside. He want that chocolate, but nothing is available into the house. So he called one of its sibling, external agent. Please do that work now. Please do that work now. External agent told lots of varieties of the chocolates are there. What I am going to do? External agent here told how I am going to balance the lots of energy variations. Source charge gave one of the criteria. Only bring the dark chocolate. External source charge gave an criteria to the external agent. Only bring the charge in such a way that its velocity remains constant and change in kinetic energy remains 0. External agent, okay, I will try to do that. And sibling to that person, okay, I will try to do that. He brings up the chocolate at the home. Okay, he brings up the chocolate at the home. So this kind of the scenario it is going on. So simply if I want to define that amount of energy required to bring an object from infinite position to a point under electrostatic field. This energy is electrostatic potential energy. Many students might be in the sir, you are bluffing us. How? In entire of your explanation and the example that you gave from the day-to-day life, nowhere you used the word potential energy. Yes, sir, you use that word external agent. Yes, sir, you use that word that external agent is doing some work. Yes, sir, you use that. It is doing work in such a way that velocity remains constant and the kinetic energy remains 0. The change in kinetic energy. But where potential energy is involved, sir? Okay. The definition that is given into the NCERT, you just wrote it down by memorizing. I have to write it down into the lecture. I have to write it down into the lecture. Huh? You just wrote it down and Allah Allah wal Habibi. Wallah Wallah al Habibi. Huh? Where potential energy is involved. The work is done by external agent. So according to the work energy theorem, this work done is being resultant into the change into the kinetic energy plus change into the potential energy. Now what happens, whatsoever the work is done by the external agent, right, it is done in such a way that velocity remains constant and change in kinetic energy is 0. Now see, whatever the work is done by the external agent, that is stored into the form of the change in potential energy. Why? The work is done against the field. Field is electrostatic field. Electrostatic field is conservative field. So whenever the work is done against the conservative field, it is stored into the form of potential energy. 11th standard 6th chapter, work energy and power. right? Work done by conservative and non-conservative forces. Whenever the work is done by the conservative forces or into the conservative fields, right, then it is stored into the form of the potential energy. So here whatsoever the work is done, okay, it is stored in form of potential energy. Whatever the work is done, right, it needs to be stored into the form of the potential energy. This potential energy, it is electrostatic potential energy. Okay. So whenever whatever the external agent is doing the work, condition is what? Velocity should remain constant and change in kinetic energy should be zero. So he is bringing up the charge from infinite position to the point under the electrostatic field in such a way with this criteria. Finally, it is doing the work against the field, electrostatic and conservative field. So in that case, what happens? In that case, work done is stored into the form of the potential energy. That is nothing else but the electrostatic potential energy. Yes or no, guys? Yes or no? Right? Yes or no? Okay. So this is the concept of the electrostatic potential energy. What about the electrostatic potential? Similar concept is there, just a bit of change. Right? Electrostatic potential, small concept, lots of change. Sorry, small change, lots of concept. External agent is a sibling of the source charge. External agent is the sibling of the source charge. So when he was buying the chocolate, okay, when he was about to start doing work, he thought, yeah, if my brother, right, is craved for the chocolates, like I think he might need more than one, like he might need more number of the chocolates, right? Yes or no? Is it possible that he might need only one? No. There is a possibility he might be in the need of the varieties. So he thought, let's not bring one charge, let's bring n number of charges. Let's do the work for n number of the charges. Let's bring the variety of the chocolates. Chocolates, not chocolates. It's variety of chocolates. Okay, variety of chocolates for it. For all of those conditions, let's bring all of those chocolates such a way that velocity remains constant and change in kinetic energy remains zero. Chocolates. Yes? Yes or no, guys? Chocolates. We have to do that. Yes or no, guys? We have to do that. So in that case, how much amount of the work he did per chocolate, per unit charge? That is nothing else but the electrostatic potential. Work done per unit charge to bring from infinite position to the point under the electrostatic field. Work done per unit charge. Work done by the sibling per unit chocolate. He brought the varieties of the chocolate from the outside area to inside the house. So what is work done per unit chocolate? Important na, guys. Work done per unit chocolate. Chocolate. Okay. So as of that reason, okay, the definition of the electrostatic potential and the electrostatic potential energy appears to be same. right? Electrostatic potential and electrostatic potential energy, the definition of both appears to be same as of that reason. One is work done to bring the charge, energy required to do the work to bring the charge from infinite position to the point under the electrostatic field. Second is energy required to do the work per unit charge. In another sense, we can also say this as delta V is equal to W by delta K, or delta V is equal to delta U by Q, right? Okay. So this is the difference of the electrostatic potential and the electrostatic potential energy. You might have understood well, right? Okay. One, energy required. Second, suppose if more number of the charges is bringing up, the external agent is bringing up, then what is the work done per unit charge? Okay. Now let's move on to the concept of electrostatic potential energy, right? For the n number of the charges, how we are going to do that? See, everything it is correlated with, everything is interlinked with the work. Okay, everything it is interlinked with the work. Work done for the n charges. Suppose again we are going to take the source charge, right? Okay, at point A, point B, point C, point D. I have to bring up the four charges. Okay, the source charge has given the task. Okay, the source charge has given the task to the external agent that here n number of charges are present. Okay, you have to bring up all of those n charges inside the electrostatic field. Right. Suppose first of all I am going to take the example for the four charges. Okay. So work is done. It is stored into the form of the potential energy. Okay. Then how we are going to define? For that, first of all use this formula to check the number of pairs. Four charges are there, na? 4 into 4 minus 1 by 2, 4 into 3 by 2, 6. We will be having the 6 pairs. 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. If we have to bring up the n pairs, dot, 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 dot. Completely depends on the, okay. But many students might be into the thought. So how you are going to define this? How we are going to find out the equation? You told us it is a work done. We accepted that it is a work done, right? But how you are going to define this potential energy? It is important, na? Okay. How you are going to define this? See, work done by the external agent, that is nothing else but the U final minus U initial. Right? Okay. So from this, okay, from this work is done against the electrostatic force. Work is done against the electrostatic force. So can I define from this? You are going to get the equation as K Q1 Q2 whole divided by R. This is the equation of the potential energy. Right? This is the equation of the potential energy. Okay. From this, how we got that? Work done is equal to force into the displacement, right? Force, it is equal to K Q square by R square dot R, 1 R will get cut. So this is the potential energy and finally we got this as our answer. Same thing. So this is the equation of the potential energy. This is a concept, this is an equation. This is how the things are getting involved. Similarly, the potential is work done per unit charge. Again, things are going to get changed. It is K Q1 Q2 whole divided by, right, R, okay, per unit charge. So one charge is going to get cancelled. So the potential is defined as K source charge whole divided by R. Right? Again, I am going to write that V is equal to K Q source charge whole divided by R. KQ source charge whole divided by R. So this is the formula of the potential. These two important formulas we are going again and again we are going to use into the equations, right? Okay. So now work done for the n charges. Brought one charge, second charge, third charge and formed here the configuration. Suppose a square configuration is formed, right? Then how we are going to do that? Okay. Okay. Let's keep it here, right? First of all, I want to define the electrostatic potential for a point charge. And guys, please mark my words. Nothing like potential exists. There is always a potential difference. Nothing like potential exists. Many students might be saying, sir, nothing like potential exists, and you are saying everything is potential difference. How? If I am going to say as because of the charge, this is a charge, as because of this charge I want to calculate the potential at this point P, I am saying wrong. If I am saying now as because of this source charge, right, if the test charge is at the point P, then there might be some work done per unit charge. We have discussed there might be some work done per unit charge to bring that from the infinite position, right, to the point under the electrostatic field, and in such a way that its velocity remains constant. This thing we have discussed. In such a way that its velocity remains constant and change in kinetic energy will be zero. Its velocity remains constant and change in kinetic energy remains zero. Okay. Change in kinetic energy remains zero. Okay. So if I want to define the potential at point P, I am wrong. There is always a potential difference. Suppose I am going to write it down. The potential at point P. So that is nothing else but the infinity, right? Final minus initial. Okay, it is always delta Vp, right? Final minus initial. Okay, initial was infinity, P minus infinity. At infinity, potential is zero. So as of that reason, delta Vp, it is going to be Vp. This is the actual sense of the potential. This makes the actual sense for the potential. Okay, if it is going to come, if potential what is going to come, right, into the current electricity, if it is going to come into the capacitor, wheresoever it will come, it is always with respect to the reference point. There is a possibility, suppose here the infinite is a reference point. So there is a possibility with respect to the reference point, at reference point the potential might be zero. At the reference point, potential might be zero. So as of that reason, we are saying potential, but the word like potential never exists. There is always a potential difference. If I am saying at P, it is with respect to infinity. At infinity, potential might be zero. There is a possibility. If I am saying at point Z, potential at point Z, no, potential difference between Z and infinity. Why? Because if the charge is present at Z, then external fallacy might have done work per unit charge to bring from infinite to point under the electrostatic field. Okay. So actual sense, there is always an potential difference because from now onwards, right, thousands of times I'm going to convey, I'm going to deliver potential, potential, potential. So at all of those times, you have to mark up a single thing into your mind. If I'm saying potential, it might be with respect to the some reference point. If I'm saying potential difference, then I'm going to define these 2 points about which I would be talking about. But if I'm saying potential, it will be always respect to that reference point where the potential would be zero. Okay. So if I'm talking about the potential, it is potential difference. If I'm talking about the potential difference, it is the potential difference. Some students might be thinking, it's not like that. Okay. My actual sense to convey the simple message to you all is nothing like potential exists. If I am saying potential, then it with respect to the infinity. It is also the potential difference only, but it is with respect to the infinity. The simple message that is I want to convey. I heartily apologize if someone is not getting, they should immediately rewind this and then move forward. Okay. So simply potential for the point charge, it is defined as KQ by R. KQ by R. If the R is a distance, right, then the potential for the source charge at the specific point P, then it is defined as the KQ by R. Now, if I want to define the potential for the n number of the charges, electrostatic potential for the n number of the charges. Okay, electrostatic potential for the n number of the charges. Okay, now what I'm going to do? Suppose let us take an example. Okay, suppose okay, to understand the concept of the potential for the n charges, I have to take one example. 4 charges are present at the vertices of the equilateral triangle. 4 charges are present at the vertices of the equilateral triangle. I have to find the potential at the center point O. Find the potential at the center point O. Yes or no, guys? So in this case, what we are going to do? The resultant potential at a specific point, as because of the more number of the charges, it is defined as V1, V2, V3 plus dot 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 Vn. This is an exact equation. Suppose here 4 charges are present. Then I am going to define as V is equal to V at point O is equal to V1 plus V2 plus V3 and plus V4. Suppose the side of the square is A. Then this distance is gonna be A by root 2 by Pythagoras theorem. This will be A root 2. Half of that A by root 2. Okay. So we are going to say the potential at 0 that can be defined as KQ A by root 2, KQ A by root 2, KQ A by root 2, KQ A by root 2. So V0 that will be equivalent to 4 root 2 KQ whole divided by A. This will be the net potential at the point A. The net potential at the point A. Yes or no, guys? Net potential at the point A. The simple example I conveyed using that. So suppose if I am saying this now, the net potential at the point O, then it is not a potential, it is a potential difference with respect to infinity. That's it. The actual message that I want to convey, it is not potential, it is a potential difference. This is not a net potential, this is a net potential difference at O. With respect to whom? With respect to infinity. Why I am not taking the infinity at the consideration? Because at that point, value becomes 0. That's why. Right? So again and again I am conveying the same message that nothing exists like a potential, there is always a potential difference. We did potential for the point charge, potential for the n charges. Now we are going to see for the potential for the dipole. A very simple thing. A very simple concept, and immediately we are going to grab up these things. I have to take one dipole. Negative charge, positive charge, This is the mid between at point P, right? I need to calculate the, right, at point P. I must say, let's take this point at, because we need, okay, let's take this as P. Okay, so can I say this distance is R1? Can I say this distance is R2? Can I say from the midpoint this distance is R? What will be the agenda? Calculate potential at point P. Calculate the potential at the point P. Yes or no, guys? Calculate the potential. This will be the agendas of today's, right? Calculate the potential at point P. Okay, as because of the dipole. This is a negative charge, this is a positive charge. Now, as because of these two charges, the potential at the point P, it is defined as V1 plus V2. For more number of the charges, directly we have to take the formula of the n charges. If more than one charges are present, immediately take the formula of the n charges. Right? Now it is important to understand the concept of distance. How you are going to calculate the R1 and R2, it is an important stuff. How you are going to calculate the R1 and R2, that is an important stuff. For that, you have to extend one line. Drop the normal. Right? Drop the normal. Okay? Whenever you are dropping up the normal in between these two lines, okay, then those two lines become similar. It means that right now this distance and this distance is same. This and this is same. In another sense, suppose if I want to convey the very single message, see, mark my word, if I want to convey the very simple message, okay, suppose if I am dropping the normal, this is R, this distance would be greater than R, this distance would be less than R. It means that R1 will be less than R, R2 will be greater than R. Simple. In this entire concept, okay, no calculation is going to hamper you. Okay, only dropping up the normal is an important concept. Only again I am going to explain you, sorry for that. Okay, again I am going to explain you. Okay, if you want to just note this down, you can do this for a while. Okay, we need to calculate the potential at the point P. Again, I am going to explain you how to drop a normal, right? How to drop a normal. Sorry for that. Okay, wrongly we dropped the normal. Suppose I am dropping a normal in this way. I heartily apologize. I am dropping a normal in this way. Okay, then this and this becomes equal. Suppose this is theta. Can I say this part as R cos of theta? So the entire part R2 will become R minus R cos of theta. I told you all, this part and this part is same. So this part will be R minus R cos of theta. That will be equivalent to value of the R2. Okay, sorry, in the previous case, by mistake, I dropped a normal into the wrong way. Now I am extending the value of R. Again a dropping normal for R1. Okay. See, If you are dropping the normal na, then those two lines becomes equal. If I have dropped the normal from 1 to 2 na, then length of these two lines will become equal. Just keep this thing into the mind. Okay, length of this and this will become equal. Right? So it means that if this is theta, this distance is r cos theta. How I am got this as r cos theta? Sorry, not r cos theta, L cos theta. I'm sorry. Okay. Okay. I think let's understand the concept from the beginning. Electrostatic potential due to dipole. I don't want any kind of the confusion for you all. Sorry. Okay. We will take more amount of the time, but I don't want any kind of the confusion. Okay. I don't want any kind of the confusion. See. Negative charge, positive charge separated by the distance of 2L. We want to calculate the potential at the point P. What is an agenda? Calculate potential at point P. This is the agenda. Right? Calculate the potential at the point P. Can I say the distance of the negative charge to that point P is R1? Can I say the distance of the positive charge R2? Can I say the distance of the midpoint to that charge is R? R1, R2 and R. These three values are different. Two charges are present. We want to calculate the potential at the point P. So our major concern is to calculate R1 and R2. But more number of charges are present, then immediately we are going to use the formula V is equal to V1 and V2, V1 plus VT to V2 to calculate the net potential at this specific point. Yes or no, guys? Right? Net potential at the specific point. Now what happens? Right? How I am going to identify the value of an R1 and R2? This is a major concern. So what I'm going to use, I'm specifically going to use the value of R and L. First of all, I'm going to drop the normal. Whenever we used to drop the normal, the two lines becomes equal. It means that value of R2 will become this much value of R. This much value of R. Can I consider this as theta? Right? If this is theta, this is 90 degree, this is L. Can I consider this as L cos theta? The whole is R minus L cos theta. The remaining will be R minus L cos theta. Yes or no? So it means that this much part of the line, right, we are able to define as R minus L cos of theta. Okay. And that part will be equivalent to R2. So here we got the R2 distance as L minus cos of theta. Okay. Now R1. I am going to extend the line. Again, I am going to drop a normal. Now, this line and this line becomes equal. By dropping the normal, two lines become equal. And whatsoever the angle they are tilted, if you are dropping the line, then a length of the, the dropping the normal always should be at the 90 degree. By whatsoever the lines may get tilted, if you are dropping the normal in between these two at the 90 degree, the length of those two lines becomes equal. Again, if I am going to take this is theta, then this distance is going to be L cos of theta. Now, this length will be R plus L cos of theta, and that will be equivalent to R1. We got R2 as L minus cos theta, R1 as L plus cos theta. According to the formula, V is equal to V1 plus V2, so that will be KQ by R1 plus KQ by R2. I am replacing the value of R1 and R2, I am taking the KQ as common, so that is 1 by R1. R1 that is defined as R plus L cos of theta minus 1 by R minus L cos of theta. Okay, so V is equal to KQ R minus L cos of theta minus R minus L cos of theta whole divided by R square minus L square cos square theta. R is going to get cancelled, so the net potential is defined as minus, right, 2KQL cos of theta whole divided by R square minus L square cos square theta, right. So again, V is equal to minus 2KQL cos of theta whole divided by L square R square minus L square cos of theta. Can I consider 2QL as dipole moment? So the net potential is minus Kp cos of theta, right, whole divided by R square minus L square cos square theta. This is the general terminology, general equation, right? Potential is because of the dipole. We did potential as because of the single charge. We did potential as because of the two charges. We did potential as because of the dipole. Now we are going to move forward for the potential as because of the charged bodies, right? Hope so you have understood this point. The major concern, see, from this formula, we understood that if you want to calculate the potential at the specific point and more number of charges are present, then we have to follow this formula. Same in this we did. Two charges were present in dipole, two charges are present. We have to calculate the potential at the point P. So what we use this formula, but our major concern was to calculate the R1 and R2. So for that reason, we took the midpoint as the reference and we take it as an R. I dropped the normal. On dropping up the normal, two lines will become equal. I took the angle. This will become L cos theta, right? So this distance will be R minus, this is L cos theta. The entire is R, then minus, so this will be R minus L cos theta, and by dropping the normal, this length and this length becomes equal. So R minus L cos theta array. R minus L cos of theta will becomes R2, right? Okay, sorry for that. I was about to forget you the Happy New Year, na? So as of that, some errors are going on. I heartily apologize. Sometimes it happens. Okay, so this is always because of the potential due to dipole. Now, electrostatic potential due to charged bodies. If you want to understand this concept, then you have to understand, if you want to understand the potential for the charged bodies, first of all, understand the relation between the electric field and potential. Because from now we are going to discuss for the shell, for the sphere, right, for the ring. Okay, lots of the communications we are going to have. Okay, lots of communications we are going to have. So we are going to do for that, right? Now slowly the critical concepts are going to come. So you have to be aware. I told you all into the beginning that I'm going to aware you all, right? I'm going to aware you all into all of those matters. So now we are going to understand the relation between the electric field and the electrostatic potential, right? Suppose, example, I want to correlate that example of a water to day-to-day life. Suppose electric field, the uniform electric field is directing like this way. Okay, this is the direction of the uniform electric field. In the uniform electric field, the electric field lines are parallel and equidistant with respect to each other. The electric field lines are parallel and equidistant with respect to each other. Now what happens here? I am talking about that set of points, mathematically locus of points. Don't move on to that much in mathematical way. Set of points. See, electric field for a charge is kq by r square. Potential for a charge is kq by r. Suppose here source charge is there. Now many students might be into the thought, sir, nearer to the source charge field are radial. Yes, I am talking about very far away from the source charge where electric field lines becomes parallel and equidistant. Okay. For the source charge, electric field is kq by r square, potential is kq by r. So can I say that E is equal to V by R? E is equal to V. Simply mathematically, conceptually I am not moving on. Mathematically I am going to define you the relation between the electrostatic potential and the electric field. Now what happens here? From this relation, there exists some set of points. Here potential is V1, here V1, 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 V1. Here value might differ. Why? Because here the distance is R1, here distance might be R2. Things may get differ. So I am naming it as a V2, 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 V3, 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 V3. Like this way, the common set of points having the same potential forms a imaginary surface that is equipotential surface. The word itself states that equipotential surface. Sorry. Today lots of disasters are going on. The common set of points having same potential, same into the water. Whatsoever the round ripples are generated, they are nothing else but the equipotential surface if we are talking in terms of electrostatics. They are nothing else but the equipotential surfaces. This entire is one equipotential surface. This entire is one equipotential surface. This entire is another equipotential surface. Like that way, the common set of points having the same potential from the imaginary surface, those are nothing else but the equipotential surfaces. A common set of points having same potential. A common set of points having the same potential. Okay, a common set of points having the same potential forms the imaginary surface. This is nothing else but the equipotential surface. Right? This is nothing else but the equipotential surface. Yes or no? Okay. For the uniform electric field, equipotential surfaces are plane lines. These are the equipotential surfaces. These are the equipotential surfaces. Yes or no? For the point charge, okay, these are the common set of points where potential is V1. These are the common set of points where potential is V2. These are the common set of points where potential is V3. Right? So these are nothing else but the equipotential surfaces. These are nothing else but the equipotential surfaces. Yes or no? How equipotential surface is going to help us in understanding the relation between the electric field and electric potential? Suppose this is one surface I am talking about. Okay. This is another surface I am talking about. This is third surface I am talking about. Here the potential is V. Here somewhat the potential might have increased, delta V. Here the potential might have somewhat more increased, 2 delta V. Okay. Potential is V. V plus delta V. V plus 2 delta V. Potential might have increased more. Right? Potential might have increased more. Okay. Electric field. Two most noteworthy points here with this relation. Electric field is always perpendicular to equipotential surface. Electric field is always perpendicular to the equipotential surface. Right? Second, electric field, okay, the direction of is from higher to lower potential. In this case, if you want to define the electric field is always perpendicular to the equipotential surface. Electric field is always perpendicular to the equipotential surface, and the direction of the electric field is always from higher to lower. This is higher, this is lower than the previous one, this is bit lower. If these three surfaces are equipotential surfaces, right? If these three surfaces are equipotential surfaces, right? Okay, then electric field should be perpendicular to them. This will be the direction of the electric field. Higher to lower potential, perpendicular to this is an equipotential surface perpendicular to that. And from this, if we want to define, suppose this distance between the two equipotential surfaces is defined as R. Delta R is the distance between the two equipotential surface, and I must define the electric field as negative of del V by del R. For very small change, it is del V by del R. This is just for electric field in one dimension. Electric field in one dimension. Okay. Electric field in one dimension, I am going to define the relation of electric field as del V by del R or negative of delta V by del R. This is for very large change. This is for very small change. If I am going to define general for 3D, then net electric field is equal to Ex of I plus Ey of J plus Ez of K. Okay. And in this also, suppose if I want to define this, then there is negative of del V by del X of I, negative of del V by del Y of J, negative of del V by del Z of K. So this is nothing else but the electric field. So this is the general formula applicable to all cases. This is the general formula that is applicable to all of those cases. This is just for the 1D. Don't worry, we are going to see some of the sums based on it. Right? We are going to see some of the sums based on it. Yes or no, guys? Okay. We are going to see some sums based on it. Yes or no? Okay. Right. The relation between the electric field and the potential, it is important because the entire capacitor is based on this concept only, right? The equipotential surfaces, right? For this, the electric field is radially outward, na? This is the direction of electric field. See, it is perpendicular to the equipotential surface, na? Okay, it is perpendicular to the equipotential surface. The surround are spherical equipotential surfaces. These are the plane equipotential surfaces. Like that, cylindrical equipotential surfaces, lots of things are there. Right? Yes or no? Lots of things are there. Okay. Now, on basis of C, again I want to remind you all, after that we saw the relation of the electric field and this. Okay, and we saw the relation of, this is the most important formula that will be used in sums. It is always difficult to correlate the theoretical part with the numerical. So that is why I am saying this is the most important formula. And in this, mostly the concept of partial differentiation is involved. The concept of the partial differentiation you have seen into the 11th standard, first basic mathematics, second you have seen into the work, energy and power. Wherever conservative forces and conservative fields are there, work is done into the form of potential energy. In all of those cases, the partial differentiation is involved. Okay. Why? Partial differentiation and a differentiation difference is no this thing. What we can say? No this thing. Partial differentiation and a difference. No chain rule is that. Sorry. No chain rule is there in partial differentiation. The static potential right for the charged bodies. Okay. Electrostatic potential for the charged bodies. So guys, I must say electrostatic potential for the charged bodies. Okay. See, practically speaking, only one formula is going to help you all in this. The relation between the electric field and the potential, that is defined as del V by del R. Only this relation is going to help you all in understanding, right, the value or the variations of the potentials nearby the charged body. Okay. Why? because from this negative of del V, that is equal to E dot del R. So V is going to be integration of E dot del R negative. So this formula is going to help us in understanding to find the variations of, right, variations of the potential with respect to R, right, around the charged bodies. Around the charged bodies. Anyone apart from this? This is the formula. That is the reason behind the meme, the suspense that we are going to reveal into the short period of time. Okay, so hope so this formula is okay. We are immediately moving on to the content. First, we are going to see the electrostatic potential. First, we are going to see for the electrostatic potential, right, for a shell. Electrostatic potential for a shell. Shell. Electric field equation for the shell we have seen. Electric field equation for the conducting sphere we have seen. Electric field equation for the non-conducting sphere we have seen. Okay. Similarly, electric field equation for the ring and lots of charged bodies we have seen. But among all, some of the important bodies we are going to see. Okay. Things are going to come. Don't get worried. This is a shell. The radius of the shell is R. Radius of the shell is R. We all are aware of the shell that charge is only distributed on the surface. Charge is only distributed on the surface. Right? Charge is only distributed on the specific surface. Right? So I must say in this case, first, 3 points we have to find the potential. The first one will be point A, that is inside the shell. Second will be the point B on the surface of the shell. Third with the point C, that is outside the shell. Suppose if I am using the Gauss law, I am taking one Gaussian surface, okay, of the radius R, that is inside the shell. So first, potential inside the shell. Potential inside the shell. So I want to tell you all, inside no charge is there. Shell is having the vacant space. So inside no charge is present. This thing we have discussed into the previous lectures. If there is a cavity, there is a vacant space, always the charge is zero. Charge is zero, there is no field. So if electric field is zero, it means that del V by del R is going to be zero. This terminology is going to help us in understanding the concept. This terminology tells us, right, differentiation of any physical quantity is zero. Here, if electric field is zero, then by the relation dV del V by del R is getting zero. Here, why the differentiation of the potential is getting zero? Mathematically, differentiation of any variable or any physical quantity, if it is getting zero, it means it is constant, sir. It is constant. So if del V by del R is going to get zero, it means somewhere inside the potential is constant. Potential is constant. Electric field is zero. From the relation del V by del R is zero. So differentiation of any physical quantity, if it is coming up as zero, yes, it might be it is constant. Right? On surface, we all are aware of V is going to be KQ by R. Okay, because the electric field is KQ by R square. And outside, again, by the same relation, if you want to tell, okay, then this will be the radius, that is small r, Okay, outside the potential will be, right here I am going to write it down this side, because the importance is of the inside only, right? Outside, that is equal to kq by small r, right? Yes or no? Let's draw the graph. Potential versus R. I'm going to take some values. We took a Gaussian surface now, right? Inside electric field is 0, potential is constant. Inside electric field is 0 from, see at the center everything is 0. Okay, but nearby to that up to an edge the potential is constant. Okay, so this is the value where small r is greater less than r. This is the point where small r is equivalent to r, and this is the area, right, where small r is greater than r. Okay, so in this inside section the electric field is 0, potential is constant. So can I say that potential value is constant, that is equal to kq by capital R. At the surface we are having the same value as kq by capital R. Beyond this, voltage inversely varies with respect to the small r. So the graph moves like this way. This is an actual graph of the variation of the potential of a shell, right, with respect to the distance. The single relation, the single meme we used. The same thing, we are not going to waste time for the conducting sphere, because same thing happens for the conducting sphere. Whatsoever it is for shell, same thing happens for the conducting sphere. So I am writing down the statement here. Okay. Same happens for conducting sphere. The difference is of non-conducting sphere. Because, see, if you want to just note this down, I'm moving aside on the countdown of 10 seconds. It's 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. The difference is of the non-conducting sphere. Why? In non-conducting sphere, on the conducting sphere, the charge is only present on the surface. While in non-conducting sphere, the charge is inside and outside. Charge is inside and outside. Yes or no, guys? Charge is present inside and outside both. So in this case, a simple message that I want to convey, for the conducting sphere, everything is going to be same like shell, because inside electric field is 0, potential is going to be constant. At surface, it is going to be kq by r. And apart from that, far away from the surface, it is going to vary, right? It is going to vary as in the inverse relation with respect to r. Non-conducting sphere. Charge is present inside and outside both. Charge is present inside and outside on the surface. Outside, it means, sorry for the, right, on the surface. Charge is present on the surface and inside both. Yes or no? So here, two things are again going to be same. In this also, only one thing we are going to change, that is potential inside, it will get changed. Potential at the surface, it is going to be same, that will be kq by r, right? And potential outside, okay, it will be defined as kq by small r. This is gonna be same only. Okay, the thing that differs will be the potential inside the non-conducting sphere. Potential inside the non-conducting sphere. Yes or no? If you want to just note this down, come on everyone. If you want to just note this down, you can. Come on everyone. Okay, because I need a complete attention now. I need a complete attention here. Okay, suppose inside I'm talking about a surface that is having the radius of small r, the radius of the shell is capital R. Here the potential at the surface, it is going to be kq by, right? The potential on the surface, it is going to be kq by capital R. Now, what will be the electric field inside? See, we are having only one relation to find the potential. The easiest way is like that. Okay, easiest way is we are going to use the relation electric field, that is equal to del V by del R. Electric field is going to, right, we are going to use the equation A is equal to negative of del V by del R. Okay, negative of del V by del R. So see what happens here. Again, sorry for this one. Electric field inside varies as kq whole divided by capital R cube dot R. Many students might be into the thought, sir, how you reach up to this equation? Just accept it. Okay, because that is a quite complex logic behind it. So we are not interested. Because even we are not interested into the derivation, only the equation matters. Equation matters, but it's okay. I'm going to move forward. It will help us, right, to be fundamentally strong. Okay. So suppose if I am using this relation del V is equal to negative of E dot del R, so potential, okay, integrating on both sides. Okay. Del V is equal to negative of integration of E dot del R. Okay. What point to what point we need to find potential? Suppose if we are saying this 1, then in between 1 and 2 we have to find the potential. So this is the potential inside, right? 2, potential on the surface. The point where you have to find the potential from that, the surface is taken as the reference, right? Surface is taken as the reference. Okay, and here we are going to say limit will be small r to capital R. Here the radius will be small r. Okay, so indirectly we are talking about the potential of this part. Are we talking potential about this part? We are cutting out right from the entire sphere, the green part I am cutting out. So we'll get the potential of the inside. Okay, this reverse psychology we are talking about. Okay, so further integration of del V moving on from V inside to V onto the surface, that will be is equal to integration of E dot dr moving on from small r to capital R. Okay, so here this is going to be V of small r to capital R. You can say it. We can replace it. Okay, V minus V of S, that is equivalent to integration of kq by r cube dot r, okay, into del r. Okay, I am sorry, here the limits will get replaced. Okay, I heartily apologize for that. The limits will get replaced. By mistake I have written, okay, into the inverse manner. Okay, this will be Vs and this will be V onto the inside. Okay, I'm sorry. I have written, I heartily apologize for. Sometimes it happens, but the derivations are like that only. Okay, so this is going to be V plus Vs plus integration of kq by r cube dot r into del r, limiting from 0 to like this way. Okay, so on solving this, final the potential I am replacing, see, kq by capital R plus integrating small r to capital R, that is kq by r cube dot r dot del r. Finally, the potential value inside, that is coming upon as kq whole divided by 2r 3 minus small r square by capital R square. This is the perfect answer for this specific question. Right? So inside, the variation of the potentials are measured like this way. Inside, the variations of the right? Potentials measure like this way. Now let's see the graph. Graph will tell you everything. Okay, suppose, okay, we need to identify the potential versus R graph. Right, potential versus R graph. Inside, let's say R value is less than R. This is the point where R value is going to be equivalent to R, and this is going to be R greater than R. Outside we are aware of, see, at the surface we are aware of the point. It is going to be, right, at the surface we are aware of this point, that it is going to be, okay, KQ by R. But inside the variations are, the variation of the potential inside, right, that is defined as KQ by 2R, 3 minus small r square by capital R square. Right? Yes or no, guys? Okay? Yes or no? So, how we are going to? At the center, what will be the value of the R at center? 0. So, V inside, it will become 3KQ by 2R. So, center, the value of the potential is 3KQ by 2R. At the edge, it is KQ by R. So, value of the potential is getting decreased. Okay, value of the potential is getting decreased. So here we are having 3 by 2 KQ by R, and here we are having KQ by R. So the graph decreases like this way. Right? The graph decreases like this way. Okay. Now, beyond this, at this surface, we are having V is inversely proportional to R, right? So the graph is like this way. Okay, so this is a perfect, right? This is the perfect graph. Okay, this is the perfect graph. If I want to draw it into the most accurate manner, this was just for the explanation purpose, right? Then it will be like, yes. Okay, this is a perfect graph of the variation of the non-conducting sphere. Same thing happens for ring. Electrostatic potential for the ring. Okay, we need one only simple slide, then we are moving forward fastly. We'll move forward on the sums. We need one explanatory slide, right, for this ring. Electrostatic potential for ring. Right, electrostatic potential for ring. See now, this is the ring of radius R. At point P, you need to calculate the potential. Right, ring having the charge distributed on it. How the potentials are getting, like how they are varying. So for that, I have to take one small elemental charge again, dq. I have taken one small elemental charge dq, right? They are subtending the angle. Okay. This is Z, this is R, right? Okay. Let's take it a very small element dq, or you will get confused. Okay. This is a very small element dq. Okay. So this will be, distance will be under root of r square plus z square. Okay. If suppose you are calculating this is theta. Okay. If you are calculating this as theta, then how you are going to find the electric field variations? So the electric field variations are calculated as, again the same relation we are going to use, del V by del R. Okay. Again the same relation we are going to use. So here you are going to have it at del V is equal to E dot del of R, right? Or if you don't want to move on to this relation, then we are having the another method also. Directly we are able to calculate the potential, as because of this dq, okay, the potential at that specific point is defined as dq is equal to k dq whole divided by distance of under root of r square plus z square, right? Okay, dq, can I replace it as del v is equal to, can I replace it as lambda is equal to dq by dl? Can I replace this dq as lambda dl under root of r square plus z square? Now the width is, right, angle is d phi is equal to arc upon radius. Arc is dl, radius is r. So can I replace dl as r of d phi? The common procedure, right, that we are following, okay, that we have already seen into the 7th chapter, 11th, okay, rotational. So del v, that is equal to k lambda, okay, r d phi integration of under root of r square plus z square. Okay, so if you want to integrate on both sides, okay, if we want to integrate on both sides, then we will be integration of 0 to 2 pi, okay, k lambda r d phi whole divided by under root of r square plus z square. So this is gonna be v is equal to, okay, 2 pi k lambda r whole divided by under root of r square plus z square. This is the variation of the potential while moving on from the center to that point. Okay. At center, if you want to calculate, you can make it, right, z value as 0. Okay, at center z value is 0, so we are going to get it as 2 pi k lambda r whole divided by r. So this r is going to get cancelled. So v at the center, you are going to get it as 2 pi k lambda. Okay, I think it is a constant value. At the center, it is a constant value. Okay, so this is how the potentials are calculated. I'm moving aside. This is how the potentials are calculated. Okay, one thing you might be having the doubt that how we took this calculation. Don't get worried. You can again rewind this video and just check it out. Okay. Capacitor. What actual the capacitor is all about? What is the main purpose of this device? Okay, because capacitor, it means that maximum number, not maximum, all of the students are only having a single scenario. What kind of the single scenario? It is only the parallel plate. No, capacitor is not only the parallel plate capacitor. Lots of capacitors, right, are there. But the main purpose of this device, right, is to store the charge. Many students might be right thinking, sir, how it is possible to store the charge? Any device is only having the capacity to store the energy. Okay, but it is with the purpose of the charge. It is with the purpose of the charge. So if I'm going to talk about the general explanation of the capacitor that has been not given till now, this is not a technical definition. Okay, okay, this is not a technical definition. I'm going to tell you all. The capacitor is the device. The capacitor is a device. I'm writing it here. This is the important statement that you have to move on. Capacitor is a device capacitor is a device that has two plates of any, again I am going to correct myself, It has two. What kind of two? Okay. Capacitor is a device that is having two conducting materials separated by insulating medium. Two conducting plates of any arbitrary shape and size two conducting plates of any arbitrary shape and size separated by insulated medium. This is the exact definition of the capacitor. The capacitor is a device that has two conducting plates. These conducting plates can be of any arbitrary shape and size, right? If they are square plates, it will be parallel plate capacitor. If those are spherical plates, right, then it will be the spherical capacitor. If those are cylindrical plates, it will be the cylindrical capacitor. These two plates are conducting plates. One is having the positive side charge, second is having the negative charge. They are separated by this, right, insulating medium in between them. They are having insulating medium in between them. This kind of the arrangement, it is known as capacitor. Okay. So this is the actual formula. This is the general formula of the capacitor that everyone is talking about. General formula of the capacitor that everyone is talking about. Today we are only going to discuss the maximum amount of the theory part, right? Because questions from the capacitor are completely interlinked. At any point, question may come from the fundamentals. At any point, question may come from anything. So today we are only going to discuss the theoretical part. Today we are only going to discuss the theoretical part. Yes or no? Okay. So, hope so the actual definition of the capacitor is clear in front of you all. It is a device. Okay. It is a device. It is an arrangement that is having the two conducting plates of any arbitrary shape and size. This can be of any arbitrary shape and size. Right? Separated by the insulating medium, this entire arrangement, it is known as capacitor. Second, the main purpose of the capacitor is store the charge in form of energy. The main purpose of the resistor is to resist the flow of the current. How you are going to measure its resistance? Ohm. The main purpose of the capacitor is to store the charge in form of the energy. How you are going to measure its capability? How you are going to measure its capacity? By capacitance value. Capacitor has capacitance. The unit of the capacitance is farad, but what actual the capacitance is all about? The capacitance is nothing else but that will show that this arrangement can store this much amount of the charge within it, or this arrangement can store this much amount of the charge in this much form of energy within it, right? So this is the main purpose of the capacitor. This is an actual definition of the capacitor, and this is how its capacity is measured. That is capacitance. Unit of the capacitance is farad. Basically, we are having the three types of capacitors. Basically, we are having the three types of the capacitor. The first one, right? Okay. If I told you all about the capacitor is an arrangement of these two plates separated by the insulating medium, but these plates can be of any arbitrary shape and size. So similarly, I'm going to convey the single message to you all, right? The first, that is a cylindrical capacitor. Cylindrical capacitor, in another sense, it states that cylindrical capacitor, in another sense, it states that those two plates can be of any arbitrary shape and size. I am taking, right, that as cylinder. Okay, this is the positive charge. One plate is having the positive charge, one is negative charge, and in between these two we are having the insulating medium. In between these two we are having the insulating medium, yes or no? So this kind of the arrangement, it is known as what? Cylindrical capacitor, right? This kind of the arrangement, it is known as what? Cylindrical capacitor. Okay, now second type of the capacitor, it is nothing else but the spherical capacitor. I am talking about the two spheres. The one is having radius A, second is having radius B. I am talking, this is the outer part of this sphere. It is broken from inside and another sphere is kept. Okay. Inside sphere contains the positive charge, outside sphere contains the negative charge. Inside sphere contains the positive charge, the outside is part of the sphere, right, contains the negative charge. Yes or no, guys? And it is separating by this, you can see this vacant space. Okay, this is the vacant space you are saying, this is nothing else but the insulating medium, right? So this kind of the arrangement, it is known as the spherical capacitor. The third most important arrangement, it is going to come upon as parallel plate capacitor. In this entire chapter, maximum part, we are going to deal with the parallel plate capacitor, right? Spherical capacitor, cylindrical capacitor, right? The parallel plate capacitor. Parallel plate capacitor is nothing else. Those two plates, if are separated by, right, the insulating medium, the one is having the positive charge, second is having the negative charge, and we are having in between the insulating medium, then this kind of the arrangement, it is known as what? Parallel plate capacitor. 2, 1. Yes or no, guys? Hope so you have stored it. Okay. Steps to find the capacitance for all. Steps to find the capacitance for all kind of the capacitor, and I'm going to prove that also, don't get worried. I am going to prove that also. The first step, okay, just note down positive and the negative plate of the capacitor. Step 1. You have to just note down the positive and the negative plate of the capacitor. Second step, find out the net electric field between the plates of the capacitor. Note down the positive and the negative plates of the capacitor. Second, find out the net electric field, right, in between the plates of the capacitor. Third, by relation V is equal to D. D is the separation between the plates. I'm going to prove it, don't get worried. By this, find the potential, and by Q is equal to CV formula, C is equal to Q by V formula, right? Find the actual value of the capacitance. These are the 4 steps that is common in all. That is common into the cylindrical capacitor, into the spherical capacitor, right? Okay. into the parallel plate capacitor. Don't get worried, I'm going to prove that. Don't get worried. Okay. First, we are going to prove for this for the parallel plate capacitor. Why? Because that thing we are going to use a lot. Okay, that thing we are going to use a lot. So, parallel plate capacitor states that capacitance for the parallel plate capacitor. Then I will prove for the spherical capacitor and give you all homework to prove for the cylindrical capacitor. Okay, parallel plate capacitor. Parallel plate capacitor. See, note it down. This is the positive plate. This is the plate where negative charge gathers. This is the distance between the two plates. Okay. Step 1, I have successfully noted this down. Which one is a positive plate? Which one is a negative plate? Step 1 successfully completed. Step 2, find the net electric field into that insulating medium. If this is a positive charge, this one is a negative charge, and there might be some electric field in between these two, na? There exists the electric field in between these two. So suppose I am going to take one point. Okay, suppose I am going to take one point. This is the point where I have to find the net electric field. It is very simple. Okay, this side it will be electric field as because of the positive charge. Again, this side electric field as because of the negative charge. So the net electric field that will be equivalent to electric field as because of positive charge, electric field as because of the negative charge. So this is sigma by 2 epsilon 0, sigma by 2 epsilon 0. This thing we have seen, the equation for this plate kind of thing we have seen into the electrostatics, right? So second step is to have the net electric field in between the plates of the capacitor. So it is sigma by epsilon 0. Okay, sigma is nothing else but the surface charge density, because here the plates are of 2D. So can I say it is charge per unit area into epsilon naught? This is the net electric field. Can I consider this as equation number 1? Second step we successfully completed. Third step, we have to move on. The net potential D is the distance between the plates of the capacitor. Replacing this, you are going to get Q by A epsilon naught into D. This is the potential we got. Can I consider this as equation number 2? Third step we successfully completed. Fourth step, second step, third step. Now, C is equal to Q by V. Q D epsilon naught A. Q will get cut. The capacitance of the parallel plate capacitor is defined as this way. Capacitor of the parallel plate capacitor is defined in this way. Yes or no, guys? Okay. Capacitor of the parallel plate capacitor is defined into this way. C is equal to epsilon naught A by D, where epsilon naught is permittivity of the medium. Permittivity of the medium in between the plates. Permittivity of the medium in between the plates. A is the area of plate. D is the distance between them. Right? On what factors capacitance may rely? Okay, capacitance of the spherical capacitor. Right? Capacitance, okay, identify the positive plate and the negative plate of the capacitor. This one is the positive plate, This one is the negative plate of the capacitor and it is separated by the insulating medium. This is the inner radius, right? And this one is an outer radius B. Okay, why I kept it is actually in mid between. For the understanding, for the explanation purpose, I have kept in side. Step 1 successfully completed, right? Step 2, take a Gaussian surface to find the net electric field, because in this case without Gauss law we are not able to find that electric field. So let's take one Gaussian surface whose radius is r. Okay, one Gaussian surface whose radius is r, and suppose if you want to find out the potential, then it is E dot del r. Okay, the electric field is, as because of the Gaussian surface, can I say it is K? Okay, the charge on the Gaussian surface Q whole divided by small r square into del r. This Gaussian surface can minimum shrink up to the radius of A. That is the positive plate of the capacitor. It can maximum go up to the outer radius B, that is the negative plate of the capacitor. In between this two, we are having the insulating medium and the energy is stored within it. So the radius will be A to B. Okay. C is equal to Q by V. By integrating this and replacing in this, you are going to get it as 4 pi epsilon naught AB, right, whole divided by B minus A. This is the capacitance for the spherical capacitor with inner and outer radius. This is with inner and outer radius. It is with inner and outer radius. Suppose if I am talking about the spherical capacitor that is having only the single radius, okay, then capacitance value is defined as C is equal to 4 pi naught, 4 pi epsilon naught R, right? Okay, so see, same steps we took to find out the capacitance for the parallel plate capacitor, right? To find out the the capacitance for the spherical capacitor. Now I'm going to give you all for the cylindrical capacitor. I'm going to give you all as an homework. Cylindrical capacitor, right? Okay, I'm going to give you all as the homework. Okay. This is the positive plate. Right. The negative plate within it. The value that is of the capacitance you have to find in between. Okay, guys. So this is the rectification purpose, right? That whatsoever the steps, the same 4 steps we are going to use to find the value of the cylindrical capacitor. But it is important for you all that you should understand. Okay, you should rectify yourself whether you are able to solve or not. Because if any critical thinking question will come up into an examination, you will get stuck. Okay, so it is important to check it out whether you are able to solve it or not, right? So this is a homework from my side. Same steps you have to follow, guys. And you have to answer this homework based question beneath the video. Right? You have to answer this homework based question beneath the video, right? Okay. Now, directly we are moving forward, okay, to the energy stored inside the capacitor. In entire lecture, I told you all, capacitor stores charge in form of energy. Right? Okay, this. From now onwards, we are only going to have the parallel plate, capacitor, and all of those stuff only, right? Okay, so first of all, the parallel plate capacitor I am talking about, how you are going to see, first of all, two important questions are going to come up into the mind of each and every student. How energy is stored, where energy is stored, two words. How much amount of the energy is stored, we should be any measurable mathematical expression. We want any mathematical expression through which we are able to identify the energy stored into the capacitor, and where energy is stored. We are not able to see any kind of a space where energy is able to, the device is capable to store the energy. So first of all, again, I am going to take this as a positive plate of the capacitor, right? This as a negative plate of the capacitor, the plus Q and negative Q. Okay. So the simple thing that I want to convey in front of you all, okay, the simple thing that I want to convey in front of you all is, okay, I'm going to decrease the plate size because we need a lowermost area for the explanation purpose. Okay. Sorry for that. I'm taking your time, guys. Okay. See, positive. The first question, the answer to the first question, the energy is always stored, right, in electric field that is developed inside the capacitor. First, okay, energy is always stored, okay, inside the electric field in between the plates of capacitors. Hello, right? Whatsoever the electric field that is produced in between the plates of the capacitor, right, energy is stored within it. To find out, okay, I told you all how much amount of the energy is stored and where. I have answered where. The large amount of the electric field that is developed in between the insulating medium, the two plates of the capacitor, the high amount of the energy is stored. Slowly, when the external capacitor is disconnected, it will get discharged. Basically, with the capacitors, two phenomena are there: the charging of the capacitor and the discharging of capacitor. Charging of the capacitor and the discharging of the capacitors, right? Energy stored into the capacitor. Okay, energy is stored into the capacitor. Okay, suppose if I see, first of all, where it is stored, I have answered. Now I am going to answer how much amount it is stored. Suppose I am going to take one example. I am going to take a charge dq. I have given the work to external agent because against this electric field I have to do the work to store the energy. Okay, I have to do against. So for that, again, I need an external agent. So I have given the task to an external agent. Take dq from negative plate to positive plate against the net field. From negative to positive plate against the net field. So external agent said that if I have to take dq, right, if I have to take dq, then work will be done. Work will be done. Paisha. Okay. Work will be done. Work will be done. So he said, okay, the work done is equal to V dq. Cool. You can do your work. Capacitor told him, right? You can do your work. If you want to do your work, I will give you the potential. Yeah, you can replace. Okay. If you want to do your work, it is V dq. Okay. You can replace it by Q by C. Now this work done is against the field. So as of that reason, it is stored into the form of the energy. This thing I'm not going to discuss again and again because this thing we have discussed it to the. So U is equal to integration of Q by C dq, right, from 0 to Q. So the energy stored into the capacitor, it is going to come upon as Q square by 2C. Right? This is energy. Right? So first thing, the simple thing that I want to convey, in yesterday's lecture, I told you all, from now onwards, we are going to do lots of experiments within capacitor. We are going to connect them into the series and check it out. Arre, yaar, this thing is going on. We are going to connect them into the parallel and going to check it out. Arre, this thing is going on. We are going to insert the dielectric slab. We are going to connect those battery. We are going to disconnect those battery. We are going to insert the multiple dielectric slab. Lots of things we are going to do. Generally, you are having the common phenomena, na? You just rang the bell and immediately move away. This is a kind of the funny childhood experiment you are doing, okay, to experience something. Similarly, lots of experiments we are going to do with the capacitor. I told you all, series connection, how voltage is getting divided into series. Parallel connection, how the charge is getting divided into parallel. Okay, all of those stuffs we are going to see. So first of all, let's move on to the series connection of the. Suppose two capacitors are connected into the series. This is a positive and this is a negative. Now see, this is how the battery is represented. Okay, this is a DC supply, alternating supply differs, but this is how the DC supply is represented. Suppose the two capacitor, this is capacitance C1, this is capacitance C2, right? They are connected in series. So the actual funda of the series connection is all about, right? Whenever the two are connected in series, the charge flowing through them will always be same. Charge flowing through them will always be same. So here Q is the amount of the charge that is flowing through the circuit and it is always same. I am writing down in series connection, charge flowing through the capacitors is same, right? Charge flowing through the capacitor is same. Now, practically speaking, suppose the charge going through them is same. So can I say that C equivalent, Q equivalent, that is equal to C equivalent, V equivalent? Or in another sense, if we are not following this procedure, then simply if I want to define, if the charge is getting same, then voltage are getting distributed in between the two capacitors. Voltage are getting distributed in between the two capacitors, yes or no? Right? Voltage is getting distributed in between the two capacitors. So the total voltage supply, that is equal to voltage consumed by the capacitor 1 plus voltage consumed by the capacitor 2. So in this case, suppose if I am going to replace from the formula Q is equal to CV, can I replace Q by C is equal to V? So Q equivalent whole divided by C equivalent, right? So can I replace it as Q1 by C1 plus Q2 by C2? But in this case, Q is equivalent to Q1 is equivalent to Q2 because the charge flowing into the circuit is same. So I'm going to replace this equation as Q by C equivalent, that is equal to Q by C1 plus Q by C2. So this Q is going to get cancelled. 1 by C equivalent, that is going to be 1 by C1 plus 1 by C of 2. Okay. This expression you need to follow when the capacitors are connected into the series. If we are having the n number of the capacitors, this terms extends to n. If we are having n number of the capacitors, this term extends to n. Okay. So dot it extends up to n like this way. Okay, so this was a very simple calculation regarding the series connections. Okay, a very simple calculations regarding the series connection. Okay, two most important thing that you have to remember: one, the mathematical expression of the equivalent capacitance, and second, that you have to represent the in series the charge going on in same. This is the reverse equation. If you are having the analogy of this equation with the equation of the resistors, then this is the reverse one. Okay, this kind of the equation appears in parallel connection of the resistors. The same appears in series connection of capacitors. Series connection of the equation of the equivalent capacitance in series connection of the capacitors is having analogy with the parallel connection of the resistors. Right? Its mathematical expression is having the analogy with the parallel connection of the resistors. I'm moving aside. Let's move on to the parallel connection of the capacitors. Okay. Now suppose if they are connected in parallel manner, two capacitors, right? One of the capacitance C1, second of the capacitance C2, it is connected with the external source battery, right? This is a positive terminal of the battery, this is a negative terminal of the battery. So in this case, what happens? Okay. So in the parallel connection, similarly, we are not going to waste our time, it will be quite easy. The charges are getting divided. Charges are getting divided into the parallel connection. Okay. So here suppose the Q amount of the charge that is flowing into the circuit, then this will get the Q1 and this will get the Q2. And in parallel connection, both are going to get the similar supply. So this will get the V voltages, even this will get the V voltages. So in series, voltage gets divided. In parallel, charges get divided. So what we are going to do, simple, if the charges are getting divided, so can I write it out? Q is equal to Q1 plus Q2. Q is equal to Q1 plus Q2. Now, how I want to change that? Can I replace it at C equivalent to V equivalent, Q1 to C1 V1 plus C2 V2. Now, as all of those capacitors are connected into the parallel manner, the voltages across the capacitor is same. Voltages across the capacitor is same. So, I will replace this as C equivalent into V, that is C1 into V plus C2 into V. Okay, so this V is going to get cancelled. So, the equation of the equivalent capacitance is coming out as C equivalent, that is equal to C1 plus C2. For n capacitors, this equation extends up to n, C1 plus C2 plus dot 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 plus up to Cn. Right? C1, C2 dot 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 and then extends up to the Cn. Okay? Yes or no, guys? So suppose, guys, if you want to just note this down, immediately we'll have the 10 seconds, right, to note this down. I'm giving you all the small amount of the time because after this, things are going to be quite awesome. Okay? Come on, everyone, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. You need 10 seconds for the parallel combination. You can just pause this video, right, and can move on. I'm moving aside because it will acquire the entire part. So, right, it's 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Then with this, we are having the voltage distribution and the charge distribution formula. Okay. Here, suppose the voltages are getting divided. Suppose the voltages are getting divided into the series connection, and here the charges are getting divided into the parallel connection. So, I am going to write down the formulas. Okay. Two important formulas, I am going to write it down. The voltage division formula. Okay, and this side charge division formula. Voltage division formula, and this side the charge division formula. Okay. The voltage division formula is for the series connection. Suppose two capacitors are connected in series. This thing we have seen already. Okay, and they are connected to the external supply plus minus V. Okay, so in this case, suppose you want to know what are the voltages on this one and what are the voltages consumed by this. So we are having the direct formula V1, that is equal to C2 by C1 plus C2 into V equivalent, and similarly V2, that is equal to C1 by C1 plus C2 into V equivalent. Okay, there is a proof behind it, but I think it would be, because the main focus of today's lecture should be on the complex circuits and the symmetries. And suppose if you want to move on for the capacitors, those who are connected in parallel connection, okay, and we want to find it out how charges are getting distributed within it, plus minus V. Okay, so here the Q amount of the charge that is flowing through the circuit, here it is Q1. And this will be Q2, this is a capacitance value C1, and this is a capacitance value C2. Okay, so this Q, that will be equivalent to Q1 plus Q2. Okay, so here the charge division formula is represented as C1 plus C2 into total Q, and here Q2, that is equal to C2 by C1 plus C2 total Q. Okay. So these are the voltage division formulas and these are the charge division formulas. The most important stuff that we are going to use into the complex circuits. Okay. Some of the important questions might come from this formula. So this formula holds the 50-50 importance here, practically speaking. This formula holds the 50-50 importance. Sometimes it happens that it is going to come, sometimes it happens, right, is not going to come. Okay. But if we are aware of what actually it states, then we are in cool position. If we are aware of what actually it states, then we are cool. It's gonna be awesome like that, right? Yes or no? Yes or no? Okay. So now we are moving forward to the complex circuits. Equivalent capacitance sums, and those are quite easy. But the thing that is going to come up into an examination is the concept of the complex circuits. The thing that is going to come up into an examination, that is about the complex circuits and the sums based on it. Okay. There are some formulas. Okay. From now, three important things we are going to discuss. First, we are going to discuss the parallel symmetry. Second, we are going to discuss the perpendicular symmetry. And the third method we are going to discuss, that is the voltage division formula. Okay. Three most important methods we are going to discuss. I am sorry for that. Okay. Three most important methods we are going to discuss. Okay. The first one will be parallel symmetry. Second one, that will be the perpendicular symmetry. The third one, right, the voltage division formula. Now many students might be in a thought of, so you already gave us the voltage division formula. No? For the complex circuit, this is a bit different. It is a twist. Okay. For series and parallel, for series voltage division is a different part. For the complex circuits, it is it's different. So I think we are going to discuss into the very different way. Lots of time we have different. So let's start with the complex circuits. Any complex circuits in capacitor can be resolved, right, through three symmetries: parallel symmetry, perpendicular symmetry, and path. Sums based on path symmetry are least going to come up into an examination, and the same path symmetry we are going to see into the current electricity also while dealing with the complex circuits of the resistors, complex networks of the resistors. Here we are going to see just like first of all have the command over the parallel and the perpendicular symmetries. Have the command over parallel and to the perpendicular symmetry, so it will be quite easy for you all. Yes or no, guys? Have command over the parallel and the perpendicular symmetry, so the things are going to be quite easy for you all. Parallel symmetry. In all of those, there are some steps to follow. Okay. Using these steps only, we are going to solve all of those questions. So what does the step states? What does those step states? First, identify the 2 points. Identify the 2 points about which we need to find out the C equivalent. Draw the line of symmetry. What is the line of symmetry that breaks the circuit into the 2 equal parts? Don't get worried, we are going to have the practical representation of it. Draw the line of symmetry. Third one, find how mirror image is formed. Okay, find how mirror image is formed. It is important to understand into the complex circuit how mirror image is formed. Third step. The fourth step that you have to follow, apply the operations on node. Many might be into the thoughts, sir, what kind of the operations on the node we are going to apply. Don't get worried. Slowly as usual, web series, slowly we are going to release our episodes, right? Okay, but don't get worried, everything will be revealed in this year. You do not have to wait for 7 to 8, everything will be revealed here. Apply the operations at the node, right? Fifth point, reduce the circuit. Okay, reach up to this result. These are the 6 points, these are the 6 steps to follow this, right? You need to follow to solve the sums, right, for the complex circuits. You need to follow. First, identify the 2 points about which we need to find the C equivalent, the equivalent capacitance. Draw the line of symmetry about those 2 points. Check out the mirror image. How mirror image is formed about the line of symmetry. Apply the operations on the node. Now, what kind of the operations we can do on the node? What is node? What is a branch? Okay. Reduce the circuit and find the results. Let's discuss the parallel symmetry first. Sorry, perpendicular symmetry. I'm drawing one circuit. This is one of the questions only, right? And that circuit, that complex circuit, we are going to solve using our steps. Okay, that complex circuits we are going to solve using our steps. Yes or no, guys? Okay, so let's follow one circuit. Okay, that is going to quite helpful. Sorry, yaar. All the time I'm having the habit to draw the resistors. Okay, so this time also it went on like this way. Suppose this is a complex circuit given into in front of all, right? This kind of the complex circuit is given into the question. Okay, I'm talking about the perpendicular symmetry. Same steps we need to follow. Okay, what does this steps 1 states? Identify the 2 points about which we need to find the equivalent capacitance. We have identified the 2 points. The one is a point A and point B. So our ultimate agenda is we have to calculate the C equivalent around the point AB. This will be our agenda. Okay. We have to calculate the equivalent capacitance about the point AB. Okay. Second, draw the line of symmetry. How to draw the line of symmetry? See, you have to draw the line of symmetry in such a way that circuits get equally divided into 2 parts. Mirror images are formed. All capacitance are of the C. All capacitance are identical. All capacitance are of the identical values. C. You have to draw the line of symmetry in such a way that the circuit should be get equally folded. See, suppose if I'm standing here, na, right? Equally divide me. This side, mirror images form of this side. Suppose I'm standing in front of my mirror. Mirror image, mirror image, mirror image. So what I'm in front, it is appearing in the mirror. What I'm in front, it is appearing into the mirror. So you have to draw the line of symmetry such a way. Suppose if I'm drawing the line of symmetry as, okay, suppose if I'm drawing a line of symmetry as like this way. I'm going to take the this is my line of symmetry. Now many students might be into the thought, sir, you took the vertical line of symmetry, but even this circuit can, right? Okay, this circuit can be folded with the horizontal line also. Okay, so this kind of the complex circuits, right, sums can be solved through both methods. In some sums, there is a possibility that it can be solved. You are having the 2 options, whether you can solve with the perpendicular or you want to solve with the parallel. But mark my words, always try out a way so that you can solve with the perpendicular symmetry, because this is the quite easy method. Always try out the way that you can find out this with the perpendicular symmetry. I can draw the symmetry, line of symmetry here also, but that I will explain into the parallel symmetry. Okay, I can draw it. Okay, but why I am moving forward to the perpendicular symmetry? Because parallel symmetry is having a one extra step. Okay, so second step we have completed. We have drawn the line of symmetry. Step number 1, identify the 2 points AB. Step 2, draw the line of symmetry. We did it. Step 3, find out how mirror images are formed with respect to the line of symmetry, right? This is how circuit can be folded. Okay, suppose this is an object, this is a mirror. For this capacitor, we are having this mirror. For this capacitor, we are having this mirror. For this capacitor, we are having this mirror. For this capacitor, right? Okay, for this mirror. Okay, for this mirror. Okay, so it means that with respect to the line of symmetry, why I am saying it is a perpendicular symmetry, the 2 points about which we have to find the equivalent capacitance, those 2 points lies perpendicular to line of symmetry. These are the 2 points A and B, right? The line, see, mark my words, the line of symmetry, that is you are saying onto the white line, right? It appears perpendicular to the point A and B about which we need to calculate the equivalent capacitance. If line of symmetry is perpendicular to the points, then this is a kind of the notification that you have to use the perpendicular symmetry. This is the kind of the notification that you have to use the perpendicular symmetry. We have to solve this complex circuit by the perpendicular symmetry. Don't get worried. The separate sums we are going to see. Okay, the separate sums we are going to see. So this is a line of symmetry. Okay, we identify 2 points. We draw the line of symmetry. We identify how the mirror image is formed. Okay, now the next step states that apply the operations on the node and the capacitors. What is node? This is the junction node. This is the junction node. Okay. On the line of symmetry, you can apply the operations on node and capacitors. First point. On line of symmetry, all capacitors will have delta V 0. This is the line of symmetry. Line of symmetry is considered as the equipotential. On the line of symmetry, everywhere the potential is same. It means that no potential exists around this capacitor and this capacitor. No potential exists around this capacitor and this capacitor. Potential difference across the capacitor is 0. It means no charge is going to flow. If charge is not going to flow through that branch into the capacitor, then why that capacitor is kept into the circuit? Remove it. What kind of node operations you can do? Remove capacitor, add capacitor, attach, detach the node. Remove capacitor, attach capacitor, right? Attach the node. You can separate the node also. Don't get worry. Okay. Remove the capacitor. Maximum number of the questions are going to come from the remove the capacitor. Okay, this come very least. Okay, and attach and de-attaching the node comes all the time. So first step we did what? Identify the 2 points, draw the line of symmetry, find out about the line of symmetry, how the mirror image is formed. The line of symmetry will be the equipotential. All the points that lies on the line of symmetry are on the same potential. Potential difference, same potential, it means potential difference is 0. If potential difference is 0, right, then whatever the capacitors that are lying on the line of symmetry is having the 0 potential difference. It means we have to immediately remove this. After removing this capacitor, reduce the circuit, rearrange, redraw the circuit. I am going to redraw this circuit after removing the capacitor. This is point A. Circuit is redrawn. The capacitors, those lies on the line of symmetry, are removed. See now, this is quite easy. Series, parallel, C, 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 right? C and C. The upper branch. Okay, now this circuit can again be rearranged into the point A, 3 part. The upper one, the lower one, and the bottom one. This is a B. Okay, see here, 4 capacitors are in series. C by 4, because all are identical, na? By applying the formula of the capacitors into the series. What is going to come? 1 by C, that is 1 by C, C equivalent. Okay, so that is 1 by C, 1 by C, 1 by C, and 1 by C, right? This is the same thing is going to come, na? Bottom also 4 capacitors are there, so it is going to C by 4. In between 2 capacitors are there, so we are going to have the C by 2. Now all are connected in parallel. So in C equivalent, if they are connected in parallel, C by 2 plus C by 4. I'm sorry, C by 4 plus C by 2, right? So this is going to be C by 2 plus C by 2. The C equivalent, it is going to come upon as C. Reduce the circuit and reach up to the results. Okay, reduce the circuit and reach up to the results. Okay, don't get worried, we are going to solve 2 or 3 sums based on the perpendicular symmetry, right? Again, we are going to clear up those things. Second sum. This is point number B. This is point number A. All capacitors, those are connected into the circuit, they are of the identical capacitance value. All those are connected into the circuit, they are of the identical capacitors value. Okay. So what you are going to do? You have to find the equivalent capacitance in between A and B. Boom, boom. Okay. Boom. Again, one capacitance is there, right? Now, what is going to happen here? What is going to happen? Step 1, identify those 2 points about which you need to calculate the equivalent capacitance. A and B are the 2 points about which I need to calculate the equivalent capacitance. Step number 2, draw the line of symmetry. This is the line of symmetry about which the circuit can be equally folded into the 2 parts. This is the line of symmetry about which the circuit can be equally folded into the 2 parts. On the line of symmetry, we are having one capacitor. But guys, it is quite difficult to remove. Check it out. If it is easy to detach the node, first do that. On second priority, remove the capacitor. Removing the capacitor would be on the second priority. On the first priority, that should be detaching a node. How? See, this is a node, na? Detach it. Detach it. Detach the node. First step, identify the 2 points. Second step, line of symmetry. Circuit is folded, mirror image is formed. Operations, removing the capacitors, attaching the capacitors, detaching and attaching the node. I am detaching the node. The first priority is detaching a node. Second priority is removing the capacitor. I am detaching the node and redraw this circuit. Okay, so I am redrawing this circuit. See how the circuit is redrawn. The node is detached from this to this. Detach it. Detach. C, 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 C and C. Again this circuit can be, now solve it immediately. C, C, series, parallel to this. So this can be this circuit can be rearranged like this way, A and B. This will be C and C. On this side we are having the capacitance C, on this side we are having the capacitance C. These two are in series. So the equivalent of this two, it will be C by 2. And it is in parallel with C. So this is going to be 3C by 2. Many students will be into the doubt. These two are in series. So equivalent will be C by 2. It is in parallel with C. So C by 2 plus C, right? 3C by 2. This kind of the rapid and oral calculations, you have to do it. Now these two are in series, these all are in series. Okay. So the final circuit is going to be C by 2, C by 2 will be the bottommost part, right? This is the B, this is the A. C by 2 will be at the bottommost part, this will be in series. So and these two are in series. Okay. So for this we need to calculate 2 by C plus 2 by 3C, that is 1 by C equivalent. Okay. So I think this is gonna be, let's make it 2 as common. Evaluation is only important, 1 by C and 1 by 3C. Okay. So this C equivalent, it is going to be 1 by 2. Okay, 3C dot C whole divided by 4C, right? So 1C is gonna get cancelled, so it is 3C by 8. Okay, 3C by 8. Now again these are in parallel connection, so C equivalent would be 3C by 8 plus C by 2. Okay, so C equivalent, that will be equivalent to 7C by 8. This is the perfect answer for this specific question. This is how circuits are resolved. Let me check I haven't done mistake or not. C. Okay, I've detached the node. Okay, detaching the node is good. Okay, C by 2 in series, parallel with 3C by 2. 3C by 2 and, okay, yes, we have done mistake. 3C by 2 and C by 2 in parallel. So 3C by 2 dot C by 2, 3C by 2 plus C by 2. So this will be, just allow me to check it out whether I have done any mistake or not. So this is 3C by 2 dot C by 2 whole divided by 4C by 2, that is 2C. So this is gonna get cut. It is, yes, 3C by 8 is going to come. Okay, it's perfect. Right? It's perfect. I've evaluated it, it's perfect. Okay, so this is how the steps we are going to follow. One sum I'm going to give you all into the parallel symmetry as a homework. I'm going to write it down here. This is a complex circuit you need to follow, and you have to write, find the equivalent capacitance between A and B. All capacitors are of the C. Follow the same steps, right? Okay, find the C equivalent in between the A and B. It should be compulsory by the perpendicular symmetry. It should be compulsory by the perpendicular symmetry. Yes or no? Okay, so this is a homework from my side you have to do. Yes or no, guys? Homework. Okay, you have to answer beneath the video. Now let's move on to the next question. The next concept, that is a parallel symmetry. In parallel symmetry, same steps you need to follow. But there is a disadvantage here. From the calculation point of view, if I am talking about, there is a disadvantage of the parallel symmetry. There is the disadvantage. Why? All of those sums of the parallel symmetry cross through perpendicular. If you are applying parallel, on the second step, you have to apply perpendicular. We are having no choice. So that's why I told you all into the beginning, try to solve, try to draw the line of symmetry in such a way, right? Try to draw the line of symmetry in such a way, okay, that perpendicular symmetry is applicable. Let's see the sum based on the parallel symmetry. Same sum. The first sum we are going to solve using the parallel symmetry. These are the 2 points about which, right, we need to solve. Parallel symmetry solves like into the very different manner. Okay. What happens here? Step 1. Identify the 2 points where we need to calculate the equivalent capacitance. All capacitors are of the identical. Huh? Some might be into the thoughts or what is the value of C. All capacitors are of the identical capacitance value C. Again and again, I am not going to write it down. Now this is the line of symmetry. This is the line of symmetry. Previously we took the line of symmetry perpendicular to this points. Now we are taking line of symmetry parallel to this point. See, A and B are the 2 points about which we need to calculate the equivalent capacitance, right? The white line of symmetry that appears parallel to the A and B. Previously we took line of symmetry perpendicular to A and B. Okay. So some sums can be solved using both. When this kind of the situation appears, always select which symmetry? Perpendicular. Because if you are using the parallel symmetry and then the very next step, you have to use perpendicular. So in spite of that, it's good to use directly the perpendicular symmetry. Okay. The way of solving the questions of the parallel symmetry are a bit different. In these, operations are different. In previous, we can attach and detach, denote and add and remove all of those capacitors. But here, see, potential is X. Mirror images are formed. The circuit can be folded like this way. So here, if potential is X, mirror images are formed, potential is X. Here, suppose potential is Y, mirror images are formed, potential is Y. Here, suppose potential is Z, mirror images are formed, the potential is Z. Yes or no? Okay. In the different manner. See, there is a very slight difference between the parallel and perpendicular symmetry that I am going to convey right now. You have to complete focus on this. Slight difference while solving the sum of the perpendicular and the parallel symmetry. Slight difference. X, this point, potential on this point is X. Potential on this point is X. Why? Mirror images are formed. This is a line of symmetry. About line of symmetry, the circuit is folded equally in 2 parts and mirror images. This is a potential at the C. At this point is Y. So mirror images are formed. Potential at this point is Y. Potential at this point is Z. Mirror images are formed. Potential at that point is Z. If 2 points are in the equal potentials, it means that capacitor connected to those 2 points are in parallel. Again, I am repeating. When 2 capacitors are connected in parallel, we are having same potentials. So it means that here the potential is X, right? Okay, here potential is X. It means that the potential across these two capacitor is same. Potential across these two capacitor is same. Potential across these two capacitor is same, that is Y. Potential across these two capacitor is same, that is Z. Potential across this and this will be same. Potential across this and this will be same. Potential across this and this will be same. So this will be parallel with this. 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 The upper side will be parallel with the lower part. So this circuit can be redrawn as in parallel symmetry. You have to cut half part of the circuit. Lowermost part you have to cut. You have to cut the lowermost part. Again we got a complex circuit. Again we have to apply perpendicular symmetry. This was a parallel, but this time again we have to draw the line of symmetry. Okay, again we have to draw the line of symmetry. Okay. Again we have to draw the line of symmetry and you have to follow the specific steps. Remove the resistor. So this is a parallel. After that again we have to use the perpendicular because these are the points AB and the perpendicular to that. Right? So this circuits can be rearranged as removing the capacitor. Okay, this is point A, this is point B, 2C, 2C, 2C and 2C. So this is going to be C and C, C and C. So final arrangement will reach up to point A, point B, C by 2, C by 2, C equivalent in between point A by D, they are in parallel, that is C. Same answer came. Parallel and perpendicular symmetry. मजा आ गया. Same answer came. Yes. Same answer came. So this is a disadvantage of the parallel symmetry. First, you have to reduce the circuit and again apply the perpendicular symmetry, and maximum number of the questions can be solved using both. Okay. Maximum number of the questions can be solved. Again, second homework. This question can be solved using parallel and perpendicular both. Okay. So homework. First, solve it by perpendicular symmetry. Second, solve it by parallel symmetry. Right? Solve it by perpendicular symmetry, solve it by parallel symmetry. Try to solve it by both. Try to check it out whether you are going to get the same answers or not. Right? All capacitors of the identical capacitance C. This is an awesomeness. If the number of the students, those who are getting the same answers, write comment beneath the video. Okay. Those who are not getting the same answers, please rewind and watch this video. I guarantee you are going to get the same. If you are getting the same, this concept is clear. The third method is voltage division method. Third method is voltage division method. What happens into the voltage division method? See, this kind of sums are there in examination. Sir, this kind of sums are quite difficult too. Sir, mera चकराए दिल डूबा जाए आजा प्यारे कह घबराए. Tomorrow, half of the lectures we are going to do lots of practice for these questions. Right now, suppose if this kind of the questions are going to come up into an examination, what you are going to do? This kind of the questions can be solved using the voltage division. Again, there are some steps. Select those steps. Select those 2 points about which we need to calculate the equivalent capacitance. So we need to calculate the equivalent capacitance about the point A and B. This will be our agenda. We have to find the equivalent capacitance about the point A and B. This will be the agenda. This method is like, you have to just move on, write down the potential value. 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 Again from the B side. I did it from A side. Now you have to do from B side. Move on, write down the potential value. 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 This process you need to follow. Let's start from the A. Move on. Is there any capacitor? No. Potential is A. Move on. Is there any capacitor? No. Potential is A. Move on. Is there any capacitor? No. Potential is A. Move on. Is there any capacitor? No. Potential is A. If capacitor is there, potential will change. It will consume something, na? If capacitor is not there, then all potential at all point will same. Start from B. Capacitor is there? No. Potential will be B. Move on. Capacitor is there? No. Potential will be B. Move on. Capacitor is there? No. Potential will be same. Move on. Capacitor is there? No. Potential will be same. Half problem solved. Can I name this capacitor 1? Can I name this capacitor 2? Can I name this capacitor 3? Capacitor number 1, capacitor number 2, capacitor number 3. Potential, see, analyze the capacitor number 1. Potential difference across the capacitor number 1 is AB. Potential difference across the capacitor number 2, see, it is connected to the two branches, AB. Potential difference across the capacitor number 3, again AB. The three of the capacitors are having the same potential difference. It means that the same amount of the voltages they are getting consumed. They are in parallel. First step, write down the points. Second step, individually analyze each capacitor. If I am analyzing the first capacitor, potential difference across it, AB. If I am analyzing the second capacitor, potential difference across this, AB. If I am analyzing the third, potential difference, AB. All of them have the same potential difference. Same potential difference means these three capacitors are connected in parallel. If three capacitors are connected in parallel, C1, C2, C3, the equivalent capacitance is 3C. This kind of the method need a logical approach, not calculative. The voltage division method need calculative approach, logical approach, not calculative. In parallel and perpendicular symmetry, lots of logical things are also there and calculations are there. But in voltage division method, if you are going to apply those stuff quickly, logically, very less calculation is there. Now maximum number of the students into the thought, sir, this was the very easy question you gave us. Anna, you are smart. We know you. You gave us a very easy question in which the potentials are matching at the every point. They are not getting changed. Now show us the question in which the potentials at the points are getting changed and solve this by this method. It did nothing. Just add one extra capacitor. Now what will be our agenda? Agenda will be to calculate the equivalent capacitance between A and B. Same steps we need to follow. Move from A, write down the potentials at all points. Move from B, write down the potentials on the all point. Analyze the potential at each point. Capacitor is there? No, potential is A. 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 Moving from B, capacitor is there? Yes. Potential is not B, potential is B dash. Potential got changed. You can use any of the notation you like. Capacitor is there? No, potential is there. Potential will not change. Capacitor is there? No, potential will be B dash. Potential will be D. Now resolve this part of the circuit. Analyze first capacitor. Potential difference is AB dash. Name it. This is 1, this is 2, this is 3. Right? This is the first capacitor. This is the second capacitor. Okay. Identify this thing. The potential difference is AB dash. The third capacitor. Identify this thing. The potential difference is AB dash. Potential difference across the three is same. It means they are in series. So this circuit can be, this capacitor is a separate part. We have resolved this much part of the circuit and got the equivalent capacitance as 3C. This 2, this 3C we got by solving this. This 3 are in parallel. This will be the equivalent capacitance. So students, thank you. Thanks a lot. So this was all from my side, right? I think it's time to go. Again, we're going to come back with the third chapter, current electricity. So this is your Indrajit Singh signing off from the desk. Bye bye. Sat Sri Akal and Namaste from my side. Bye everyone. Stay at home, stay safe, stay healthy amidst this pandemic and take care. Bye everyone.